IBPSA-USA. Oh, welcome everybody to this IBPSA-USA Education Committee webinar on thermal bridging. We will get started in just a moment. I'm going to wait for everyone to get their calendar notifications in their email and then join. So approximately 1 more minute. Okay, great. Well, we'll get started. So thanks again for joining for this presentation on thermal bridging and derating. Our presenter is Denis Bourgeois, PhD. He manages RD2, which supports public policy and related software, so carbon, energy, and peak demand in the built environment, and he's been doing that for more than 20 years. Denis is a long-standing IBPSA Canada member. So I will pass it over to Denis to present on thermal bridging and derating.
Thanks, Matthew, and thanks to the IBPSA-USA Education Committee for inviting me. It's much appreciated. So in the next 45 minutes, I'll be doing my presentation on thermal bridging and derating, more specifically how it relates, which is apropos to a building energy simulation. So it's a wide topic. It covers many areas, but this presentation, I'll try to keep the focus on what should concern professionals and researchers in whole building energy simulation. So I'll be presenting 5 points, starting with a background, kind of a timeline and setting up the context. Every 10 minutes, I'll stop for maybe catching some of the questions that you may have. And if not, we'll just keep progressing on the other points. So I'll start with a background. Then I'll be doing a quick overview of thermal bridging, kind of a crash course on thermal bridging. Eventually leading to its implications on building energy simulation. And then as an application demonstration, I'll be taking on 2 recent energy codes in North America that have been developed, where there's a lot of integration of thermal bridging characteristics and not characteristics, but calculations and derating. And the implementations are fairly different. So I'll be doing a compare and contrast against those two energy codes. And I'll finish the presentation on challenges and limitations beyond the presentation. What's the next steps? What are the challenges and limitations of the methodologies, regardless of the actual software implementation in practice? I'll just be trying to check. Okay, that's fine. Okay, so quick a background over the last 50, 60 years. Certainly, there's been a long-term understanding of the implications of insulation and managing or mitigation thermal bridging. The 1970s are the critical periods, of course. The energy crises led to the first very high-performance houses, locale in Illinois and the Saskatchewan Conservation House. There were more a focus on residential, and here's what it takes to fix the thermal bridging issues. Wonderful projects to study. In parallel, you would have government or large body organizations like ASHRAE starting to develop their first energy code versions. And you'd have also an industry response. Towards the late 1970s, early 80s, SHARC start distributing or producing their first commercially, I guess, patented technology. So industry is starting to respond as well. So it's not just bespoke or custom technologies or designs from engineers and architects. You're looking at industry, a nice industrial response. 1980s is more of a transition. Some of the states and provinces and municipalities are adopting the first energy codes that are being developed. Some of the first incentive programs. So there's a nice follow through throughout the 1980s, but there's not that much innovation. Certainly ASHRAE 90.1 continued to evolve. 1990s, you're looking at early 91, the first passive house certified buildings, I believe, or houses were at that time, where certainly thermal bridging mitigation was a main focus. You started noticing the first major incentive programs and next generation codes where thermal bridging mitigation starts to be part of this discussion or the dialogue, but it's haphazard. It's not super consistent. You would have a lot of exceptions in the codes. You start seeing either from Switzerland or Germany, eventually the requirements start congealing into the ISO standards 12011 or 14683. They concern direct thermal bridging. This follows through into the European Union's EPBD initiative, so that would be like 2008 and since then, so throughout the decades. And so thermal bridging, these are performance-based energy codes, and thermal bridging is a requirement. Thermal bridging mitigation and modeling. In North America, you start seeing an ASHRAE response. So you would see the research project 1365, led by Morrison Hirschfield, that led to the building envelope thermal bridging guide and subsequent codes like the NECB in Canada, NECB 2017, which is a landmark modification of the NECBs. You're seeing regional differences. The Quebec Energy Code, where I'm from, that also has a lot of requirements on thermal bridging, but they're not the same. We'll go into some detail a bit later. And you're looking at NITRA 90.1 Addendum AV for the 2019 edition, which leads to the 2022 version. So this will be a game changer for many energy modelers if you're not used to the question. Still seeing the evolution of standards like CSA Z5010, which formalizes a methodology to characterize the thermal bridging in a building. You're seeing beyond practitioner needs, you're seeing something like the Building Technology Assessment Platform by Calumet Energy and the OpenStudio standards. Together, they're doing building stock evaluations using the OpenStudio SDK, so OpenStudio engine. And so both of these organizations in tandem are starting to deploy. I'm heavily involved in that area. Starting to deploy modeling and systematic treatment of thermal bridging in their models. And there's a whole wave which, for the last year maybe, this has become more and more important, how the existing building stock, existing buildings, how they're covered in codes, rating system, digital twins, this idea of better characterizing thermal bridging, major thermal bridging in projects, and how either to mitigate them or at least have a thorough, rigorous analysis of how to treat those in building energy simulation. And of course, the initial industrial response was modest, but specific and dedicated in the late 70s and early 90s. Now we're seeing a lot more manufacturers going from insulation companies to commercial cladding clip systems. A lot more manufacturers are heavily involved in the response, I should say. If I go from left to right, spanning a 50 or 60-year period, what we're seeing is something like a move from the initial modest attempts to characterize and mitigate thermal bridging. Often it's very qualitative or descriptive. Here's the fix, here's the problem, here's the fix. As we're moving along the decades, it's becoming more and more rigorous, more and more mathematical, quantitative, and there's less and less wiggle room. If the initial requirements were limited in scope, there were many exceptions in the energy codes 20, 30, 40 years ago. Now it's pretty much all encompassing. There's not much wiggle room. There's not a lot of areas where you can say, I know thermal bridging is an issue, but as an energy modeler, I don't factor that in. That is almost impossible. Unless there's a question, Matt, I'll just skip to the second part and maybe we can ask questions if I'm moving too fast.
Yeah, we can keep going.
Okay, so crash course on thermal bridging. Most experienced energy modelers would understand the description of a U naught or a clear field effective R value, or its inverse, a U value or U naught. So this would factor in what the Canadian codes called minor thermal bridging. So these are highly repetitive elements like the steel stud, Z bars or Z bars, depending on where you're in the country or in the world. and cladding clips. And so you typically describe the representative sample, and the examples on the right would be approximately 1 square meter. You're describing the constructive principle of your, in this case, wall assemblies. So imagine a contractor or an architect trying to describe how they've built up a wall for the latest school or the latest multi-unit residential building. They'd be describing either verbally or in their specs, layer by layer, exactly what went into that wall and what the spacing would be of the various structural, main structural or secondary structural elements. And you would come up with a description and you would put that in your spec. It is usually unrelated to surface geometry. So it doesn't really matter if the floor to floor height is 9 feet or 10 feet. In some cases it will matter, but generally you're describing a construction principle. You're not describing all the thermal bridging that is considered in your building. So keep in mind that U-not symbol. From the late 90s up to now with RP 1365 and the building envelope thermal bridging guide and industrial response to this is that we introduce major thermal bridging. So these would not be the highly repetitive elements that you see in the wall assembly. These would be the major linear and point conductances. Examples would be intermediate slab edges with regards to the exterior wall, roof to wall intersections, roof parapets, cantilevered balconies, columns that are transversing the insulation of an exposed floor in the ground floor. So these are highly related to surface geometry, or the connections or the topological connections that exist between various surfaces. So a corner will be different from a roof parapet, and the floor to floor height will matter. Is the facade a highly articulated facade with a lot of bay windows and niches? This will make a tremendous difference in how significant the effect of thermal bridging will be. So we introduce, or the industry has introduced, psi factors and chi factors to represent both linear and point conductances. So instead of talking of a U-not value, we would say there's a UT or a U total. So somehow you're relating the clear field description, all the linear thermal bridging and all the linear conductances and the point conductances somehow in a single equation that you would characterize the results as being a total U. It's related simply by doing the summation of each of those points. So you would have, for a given exposed wall area, you would have a certain number of square meters. So that's your A, your area. And in that specific area would be affected by the clear field, and what would also be affected by the total linear length of each of those linear thermal bridging characterized by their own psi factors, and all this in the current, the total sum of point conductances that would affect as well the wall construction. So let's keep that equation in mind. I'll be coming often back to this equation to explain various impacts. How significant is this? Well, it depends where you are in the world and the nature of the building. I'm in climate zone 7 towards the lower limits. So that's ASHRAE climate zones. So that's about 5,000 heating degree days. This would be the same for any location that's in climate zone 6 towards the maybe 4,500. So those would be in SI units. So anyone having 4,000, 4,500 heating degree days, minus 20 C or minus 25 in terms of heating design temperatures, that would be like minus 13 Fahrenheit. You would see easily the thermal bridging requirements, or sorry, the thermal bridging coming out of linear and point conductances easily affecting by 50% the UT. Stated otherwise, if you had an R30 wall, it would not be surprising to end up with an R15 wall if you had not paid attention to the quality of the thermal bridging in your project. This does not translate directly into a 50% increase in heating. This would vary usually for climate zone 7 between 5 to 15%. It really depends if it's an internal load dominated building, a light industrial facility, maybe a call center that operates continuously, versus something like a school or a heated warehouse or a multi-unit residential building. So the range is not negligible, but the impact is noticeable. Okay. Am I going too fast or any questions? You're not getting any questions, Matt?
No questions yet. If you do have questions, please post them in the chat.
Okay. Okay, so the main focus of the webinar, kind of describe set the table, if you want, hopefully. The main focus of the presentation is, okay, so what happens now if you're trying to factor all this in an efficient way in your building energy simulation workflow? Just to be clear, this presentation will be concentrating on that specific part. I won't be describing to you how to get the latest psi factor for the latest detail from a manufacturer, or how to calculate the effective clear field R value. Assuming this is fairly well known now, or fairly well understood in the community, but if there are questions, I can help you out towards the end. So the question is really how this is deployed in building energy simulation, and are there any issues? So on one hand, you have what you typically have in a building energy simulation, which is a description of the geometry. You most likely have something that approximates the clear field by having multi-layered constructions in that model. And you would have a number of psi factors that you think as a designer or as an energy modeler, you think the architect is heading in that direction. Maybe you have an idea of the point conductances and linear conductances that you want to take into consideration. I've introduced that kind of simple equation that all this relates to, but you're not exactly sure how to affect or how to modify your building energy simulation inputs. If it's Energy Plus, it'll be an IDF file. If it's OpenStudio, it'll be an OSM file. And so there's some work to do. And eventually you will have to generate some significant or meaningful outputs for your clients, either building owners, the architects and engineers that work on the project. If I'm using the Canadian code terminology, you would have part 3 requirements, which are on building envelope. And some of the energy codes have UA, what I call UA prime trade-off mechanisms, where you do have to factor in all the major thermal bridging. Okay, that's easy said, but doing the entire math in the entire product or the entire process can be time consuming and confusing. And eventually you may want to generate, of course, your building energy modeling inputs. So that would be part 8. That would be the equivalent of ASHRAE 90.1 ECB. Okay, so what does that all mean? It's easier if I describe this in steps. So there's certainly an input step. You have your models, you have your data, you have your selection of materials. And so there's a series of characterizations, like the U-naught, the psi, and the chi factors. And then you have a series of manual takeoffs. That project that you're seeing on the left is fairly modest. You still need all the areas and all the linear, the lengths of each of those thermal bridges that would or could affect significantly the building. Current energy codes or the recent versions of energy codes don't provide you with a lot of room to maneuver. You really do have to do this. For this simple geometry, if you've done it once or twice or 3 times, you probably could get away with maybe a 30-minute extra series of steps to do that you wouldn't normally have to do with building energy simulation. So that's the entire takeoff step. If the geometry of the building is in any way more complex or larger, that becomes hours. I've had large engineering firms very experienced with building energy simulation and thermal bridging derating, and they will admit it takes them half a day, in some cases an entire day, to redo all these takeoffs if there are any significant design changes over the course of, let's say, a new hospital. That is a huge amount of work, and it's very error prone. Every time you have to do any type of manual takeoff and manual input. Okay, so the next step is a coupling phase. So you have all this input, you've done your takeoffs, you'll have to use a spreadsheet typically, and you have all that information and somewhere in the spreadsheet. Once it's there, that's pretty easy. And then you deploy this and you have your indication of what should be the final UT of your surfaces. But then you probably are asking yourself the question, am I going to have a single UT value for all my walls in my building, or should I be doing it on a surface per surface basis? Well, those are very good questions, and they have implications on the results. The third step is really, well, okay, once that's done and you've found a way to characterize your building energy modeling, building energy model, depending on your energy simulation software that you've used, you'll have to complete that step. If you're doing it on a surface by surface basis, if you don't have an automated solution for it, it'll be very time consuming. If it's something that you're doing on a facade per facade basis, that's another choice, but you'll still have to carry out those steps. So the important part is that you have numerous highly repetitive, tedious tasks that are error prone in the process. What we started asking about a few years ago was, okay, so here's RP 1365 kicking around 2011, 2012, the building envelope thermal bridging guide. And then we're noticing a lot of pushback from building energy modelers saying, whoa, this is, yes, by all means important, but if we have to do this manually every time we do an energy model, this is an issue. So, okay, so instead of trying to find workaround solutions in the energy codes, the question was rather, is there a way to automate this to the point where it's child's play? The second you put this in an energy model, within a few seconds, you can generate the entire workflow. So the first thing we're looking at is automated takeoffs. So you don't have to do any type of takeoff and use a spreadsheet. Same for the coupling. The second you start having in memory all the takeoff, let's say the quantity surveys, well, can we do the coupling automatically and then start generating directly the output towards building energy simulation models per se, so the calculation engines. And once they're done, how to fetch the information and report on, let's say, are you compliant with the prescriptive requirements? Are you compliant with the UH prime trade-off target? So we're assuming that the inputs are fine for the energy simulation model, but then we have potentially hundreds, if not thousands, of linear thermal bridges. They come at a cost. Can we automate the process as well to generate significant output so we can automate costing and do optimization? So those are the questions that we started asking my group and people that, some of my clients, I guess, we were asking around 2012, 13, 14. And some of the initial drafts of what was needed was probably articulated clearly around 2015. But it's only much later that we were able to put this into software development. For practitioners out there, there are solutions that do address these issues. Certainly IBPSA out of Sweden and Design Builder, they gave an interesting presentation yesterday on Kiva and ground heat transfer. Design Builder uses Energy Plus. IBPSA has its own calculation engine. Those are two well-known building energy modeling software solutions that do a lot of what I just described. Automated type takeoffs from geometry, the final coupling, and modification of the inputs for their energy simulation packages. They are commercial products, but they are certainly well-known and well-established solutions. There's also some tools that are integrated directly within the Revit as a Revit plugins. So these are more BIM solutions than BEM. I'm not exactly sure how that translates well into the eventual output to BEM models. Certainly the Revit MEP and Insight 360 depend on OpenStudio. So I haven't done any type of verification on that, but NumFem would be an example of a Revit plugin that would do a lot of that. We don't have an exhaustive list. We've tried to reach out with to a number of software packages over the years. We're in discussion with some major players to try to find a solution for them to catch up. But I'm not in a position to make any confirmations about where they're heading in the short term. So that's the current landscape. We publish, and I'm going to start to introduce the nature of the work that we've done. So we introduced something called TBD, or thermal bridging and derating. This had been a series of experiments and drafts dating back to 2017-18. There were a couple of white papers written on the need, and there was a special focus for open source solutions in this case. So TBD is not to be confused with to be determined. It's really thermal bridging and derating. It does the same exercise as the other packages. We published a free version, open source version in summer 2020, and it's been evolving heavily since then. So for interested users or interested readers, you can consult the RD2 github.io TBD website. It's really an online guide. It's written for, let's say, first-year university students and people more or less used to the energy simulation universe. So it's supposed to be fairly accessible, where we do explain the concepts of thermal bridging, what is the derating step, and a number of challenges and pitfalls. But it's an online guide to the use of the package. So what is it in terms of package? It's a Ruby gem and an OpenStudio measure. So for those who are used to the OpenStudio SDK or CLI, so this would be, yes, OpenStudio itself, any direct derivative coming from any of the US government labs. You also have the OpenStudio Coalition that maintains the OpenStudio application and SketchUp plugin. So they all rely on the OpenStudio SDK, all the packages that you see on screen, as well as a number of Autodesk products that I've mentioned, Ladybug tools, Cove tool, and a number of Energy Plus based workflows. It is still possible and fairly straightforward to use an OpenStudio measure with the CLI to alter the Energy Plus geometry with thermal bridging. I can go into a bit more detail on that if you have any questions. So that is possible. One example that we're working with is Hydro-Quebec with their Energy Plus CIMEB Plus software. That's not released yet, but they will be integrating TBD as a behind-the-scenes library. TBD is now distributed with OpenStudio. So from version 3.5, the gem is included. For those who are used to using the SDK in programming mode, this would be available. It remains free. It's open source, both with an MIT and BSD3 license, or there are basically 4 packages involved. So some of these are, not some of these, those licenses are probably the most permissive licenses. So any commercial application that wants to integrate it, that's fine. None of this would have been possible without my partner in crime, Dan McCumber, who manages automaticmagic.com and is part of the OpenStudio Coalition. The OpenStudio community knows Dan McCumber very well, longstanding OpenStudio developer. So we've been collaborating for about 3 years, and it's been really a blast. So Dan is more on the software side, 90% of his time. My company moves between software development in order to better support policy, and then vice versa. If there's something in software solutions that allow energy policies, whether they will have derivative products like incentive programs or new versions of energy codes, and we know there's a software solution to support this, then that's something I'm involved in. And if there's a lack or a missing part in building energy simulation that would better support codes, then I'm more on the development side. So that's how we got together. None of this would have been possible without support from both the Quebec and Canadian governments. So the National Research Council, a special shout out to Ian McDonald, who was very instrumental at the very beginning. Some of the initial workups and products were done with him. And it's been a pleasure to work with. And there's also Phil Roy Lopez and Chris Kearney, who have been very instrumental with the building technology assessment platform that is part of the OpenStudio standards package. So that was a ton of fun, and a whole bunch of people at the Quebec government side to do their own building stock assessments and to try to support the latest versions of the energy codes. So a big thanks to all of them. Okay, there's a key feature to TBD, which is the Topolis library. If you look at the building on the left, so this is the US commercial benchmark building for warehouses. It has about 300 edges. They're all drawn on the screen. What's missing from the OpenStudio / Energy Plus data model is surface edges as entities or as objects. So we infer generally the existence of an edge, and that edge could become a linear thermal bridge simply by the existence of 2 vertices, and we infer that's an edge. but we can't attribute characteristics or properties to those edges because they're not objects in memory. So this gave rise to the Topolis library. You can visit that GitHub website to have some documentation. It's also free, open source, MIT licensed. It is app agnostic. It has no idea what OpenStudio or Energy Plus or any other software package is. It has no idea what a thermal bridge is. It has no idea about costing. All it knows is geometry, and it knows something about the relationships between various edges and surfaces. It is a complete topologically consistent model, fully inspired by Wassim Jabi's topologic work. So this is called a rigorous non-manifold topology class hierarchy. And it allows TBD to retrieve edges as objects and attribute properties to them, figure out what surfaces are linked to each edge. It tags each of these edges as thermal bridges, depending on the topological relationship between each of them. And this allows TBD to make the difference or know the difference between a fenestration head, a jamb, sill. It allows it to have an idea of what's a convex corner versus a concave corner, depending on the polar angle of surfaces around each of these edges. It's very quick, so that's usually not a penalty to do this representation in parallel, but it's really a key feature, and I thank Dan McCumber for working very hard on this. So that is really a key feature for those who are interested. You can use Topolis for all sorts of other purposes, potentially for airflow, network models, for costing, very interesting. Okay, I'm going quickly into what TBD offers for those who are used to the OpenStudio graphical user interface, the app. This is what TBD would look like. So OpenStudio measures are basically plugins or macros that fit within a predefined environment that allows those to be deployed. So I am not going to go through all of the inputs. You're better off consulting the website, the online guide I mentioned a while ago. And so all of these inputs are described in great detail. Some of the interesting outputs will be some of the compliance assessments. So I mentioned something like the UA trade-off mechanisms that are part of the code. Well, TBD will generate those, they're MD files, so they're easily transferable as PDF files, but they will, if you comply, they will produce those assessments that building professionals need to keep in their dossier every time they work on a project and determine if they comply to parts of the code or not. So that's the easy part. What you may be wondering is, so I have a lot of psi factors for my model. I may have multi-layered constructions. I may have multiple constructions that characterize my building on the left. There may be a ground floor way of describing the wall constructions, and it's a completely different solution elsewhere in the building. And the geometry might be fairly complex. TBD and Topolis together try to figure out the most likely characteristic for each of those edges based on a number of rules which are pretty reasonable. But it may be, in very rare circumstances, unable to identify what the nature of a thermal bridge is, because what could be perceived as a wall is in fact a roof, or vice versa. So on one hand, we had a need to customize each of those edges potentially. And so how can we do this for 300 or 1,000 edges and still allow users to edit some of those, hopefully in a semi-automated way, so it's not a huge burden. And so we introduced a JSON file format, which allows users to specify psi sets. So if you select a construction, let's say a wall construction, most likely the psi values that psi factors that you're going to use will be highly dependent on the wall construction and the cladding system in conjunction. Both of those characteristics will determine the psi factors that you should be using. But if you're using multiple construction sets, then you would need something like this input JSON file, which would allow, in this case, I'm describing that there's a default psi set called awesome, very high performance with those values, and that's to be used by default. So if TBD figures out that one edge is something like a rim joist, which is any type of intermediate slab to wall intersection, versus a fenestration perimeter versus a cantilevered balcony, it will use those values. It will couple all of the edge lengths to those psi factors. But I can say, no, I also have a space which is called the ground floor restaurant, and it's pretty poor. And it's going to use values which are much higher, psi factors in the range of 0.7 and so on. And so the mapping between that level of resolution corresponds to the OpenStudio hierarchy. So OpenStudio allows you to define default construction sets that you can say, by default, all my building surfaces will use that default construction set: roof construction, wall construction, fenestration choices. Then you can say, well, on a building story per building story level, that changes. Or you can say on a space type basis that changes, or my housing units will be treated differently than my common spaces. And you can do this down to the individual space and individual surface. TBD follows an exact mirror to this. It will say, okay, you can have a psi set of values that works for the entire building, or on a building story level basis, or on a space type per space type basis in space, down to the individual edge. So it is possible to isolate an individual edge and say, this is not a minor transition between a minor angle difference between the azimuth of two walls that connect to each other. This is actually an expansion joint, a structural expansion joint, and there is a thermal bridging value associated to that. Here's the way to target that specific edge. So that input file is very critical. That same format is used to output every single thermal bridge that TBD has managed to identify in your model. So if you want to do costing, that output file, which may be 20,000, 30,000, 40,000 lines of information, it's not something you would read, but it's something that you can parse in a rigorous way using a JSON schema, and you would be able to fetch the total length of all the rim joists, or all the parapets, or all the fenestration perimeters. And if you have costing associated to that, well, you can do your automated costing this way. Okay. Well, I'm going to continue. I don't see that there are any questions, so I'll be continuing on the fourth step here. So as a demonstration, I'll be trying to compare ASHRAE 90.1 2022. So basically that's addendum AV to 90.1 2019. So this will be part of the 2022 code requirements. So this will affect the prescriptive requirements, ECB, Appendix G, and there are additional ways of doing those calculations. And this would be an example of what's in the standard. So you have a list of thermal bridge types. TBD will have to evolve a bit to accommodate all of those, but we're pretty much able to do this now, but there are a couple of accommodations to make. And so what you're seeing on the screen are a series of default values, that psi factor values that should be used if your building complies to code, but you would also have unmitigated values. So that's basically the architect or the energy modeler is not sure if at that stage of the design, whether they can comply to the code or not. So if you're unsure, or if you're instead convinced that you don't comply to code requirements, those values should be used. So that's the way ASHRAE 90.1 sets up the prescriptive requirements in ECB. So in short, 90.1 gives allowances on U-naught factors, so clear field requirements, psi factors and chi factors, to be used both for the design and budget building if you're using ECB. There are additional constraints like the maximum width of total width of balcony edges in your model. And what TBD would offer in that case is, okay, based on all of those and based on the linear link scenarios in your building energy model, well, here's the UT on a surface per surface basis. So TBD won't be satisfied modifying your overall building construction characteristics. It will make clone copies for each and every single surface in your model and make sure that the derating, so derating simply means you're taking all those extra conductances and you're modifying the insulating layer thickness to accommodate the effects of thermal bridging. So TBD will do this automatically. Okay, the NECB 2017 onwards is a bit different. So the U values required in the code explicitly lay out very similar thermal bridging types that I've I've shown two screens before. But the requirement is that all of those effects need to be factored in the maximum allowed U value. Therefore, it's a UT and no longer a U naught. So if you're in climate zone 7, that's an R27 in IP units. So that's a U value of 0.10. So this would apply to the prescriptive requirements as well as part 8, which is the equivalent of ECB for your proposed building. So that's the equivalent in ASHRAE of your design building. There are no additional constraints, but you do need to process all the U factors, all the U naught factors, the psi factors and chi factors in those calculations to determine if you're compliant to code. If you're using part 8, well, there's simply no major thermal bridging in the reference building. So it's kind of a perfect wall. So I'll go into some detail what this means. So since all the thermal bridging, not only the minor, but the major thermal bridging needs to be factored in, what the code is requiring is a UT. So if you want to comply to the prescriptive requirements, that your UT becomes an input. So here's my UT on that part of the equation. You have to reorganize this equation so that terms are on different sides of the equation. So the code tells you need to have a UT of, let's say, 0.21, then you have your area, and then you have to subtract from that value the linear and point conductances in order to determine in advance, because that's what you're going to put in your building specs, what kind of U naught do I need? So if it's a 0.21 and I have to subtract a number of the effect in watt per K of thermal bridging, well, that value is going to be much, much lower than 0.21. If I say this in R values, if I need to have an R value of 27, I may need as a clear field assembly, something that's offering R40, R50, R60 and up. Okay, so TBD offers a feature that's described on the online website, which is called uprating. So I'll try to explain what that means. Uprating is basically that exercise of trying to guess what the U naught factor should be once you know something about your thermal bridging and your facade layout in order to achieve the required UT requirement in the code. I'll do a couple of demonstrations for this. Maybe do you think I should be answering one of the questions before I go into detail, Matt? Or?
There is one question in the chat.
Not sure if I can use, I don't seem to be able to access this. Oh yeah, sorry. So is TBD-IO the first step in the process? So the input file, okay. It is not necessary to go through the input file or have this. This is really done for customization. You can instead just pick there's a series of default thermal bridge sets. You have the Quebec Energy Code reference and unmitigated values. Those are set in the code. You have some of the building envelope thermal bridging guide values. You have some predefined values for curtain wall technology, either high performance or low performance. So those are there to give you a range of what the effect of thermal bridging would be in your project. And that's not necessary to generate any type of JSON file. Those are preset files. You can still check here this box, write tbd.out.json. This will produce a JSON file that represents all the thermal bridging in your project. And you can use that same output file by renaming it tbd.json, and it becomes an input file. So it's the same format, it's the same entities. So you could elsewhere in this, once you output the file, you will have a series of outputs which are edges, and it will list the hundreds and hundreds, if not thousands of edges. And you can instead say, okay, those edges are referring to a psi set. I can decide it will output all the psi values for all those edges, and one can actually edit that file and relaunch the simulation, and that will work. So if you have your own custom psi set, or you've gone in some detail in the building envelope thermal bridging guide, and you've targeted, I'm compliant here, I'm not compliant there, you've come up with your own custom set. You either have to do this from scratch. You can take one of the files on the GitHub repository. You have a large number, 30 or 40 examples online. Or you can simply use the output file, which is generated, rename it, and use that as an input file. So that's pretty handy. So that's not necessary to do it every case. I wouldn't recommend this at the very beginning. I would wait to maybe do a couple of projects before you would try this. Okay, so this approach does not allow energy plus to calculate the difference in surface temperature. So there's a question whether this approach would allow Energy Plus to calculate the difference in surface temperature at a point or a linear bridge compared to the clear wall. No, the methodology follows closely. I have a hard time. All right. The methodology follows closely exactly what's laid out in RP 1365 or the Building Envelope Thermal Bridging Guide and what's required in codes, which ASHRAE, so ASHRAE Act 90.1 has two methods which are admissible. One is this modification of clear field values going from a U0 to a UT by modifying the insulation thickness as a final derating step. So that's described in 90.1. 90.1 also describes another solution, which experienced energy modelers would have been familiar with this, is to explicitly represent the effects of all the thermal bridging as what I call a wall sliver. So it's a very narrow band that you would probably add towards the near proximity of the slab edge. And these would have characteristics which are very different from the clear field assembly. Towards the end of the presentation, I discuss a bit more on this and the pros and cons. But the current method I'm describing is really more of the first method, which is, so come back to this equation, really modifying the clear field. So this would be the insulating layer in your construction, modifying that thickness or conductivity to come up with another surface UT. So, and the reason is to stick as much as possible to the current publications in either ISO or Z5010 or the Building Envelope Thermal Bridging Guide recommendations to be as close as possible to code requirements. So I'll discuss this point a bit further towards the end of the presentation. Okay, so what would be the impact of what would TBD generate for both of these energy codes? For 90.1, and this is very similar to the Quebec Energy Code. So I'm using examples, climate zone 6, this would be Montreal, Toronto. ASHRAE would require something like R20.5 in IP units. That's an SI U0 value of 0.278. And in all four cases, this is not a building that has 2 stories. This is really just, I'm comparing 4 permutations of the same facade that all have 40% fenestration to wall ratios. And in this case, I'm using some of the best details, some of the best psi factors that we have pricing on. So those are commercially available or known. Whether they're cost effective, it's another story, but those are some of the lowest values you could have in terms of psi factors. And so the difference in all cases, we have a grade edge. So that would be the wall is actually resting on some foundation. And there's an intermediate slab edge on the top. And we have 2 corners and you have a whole bunch of window perimeters. The difference between the 4 facades is the length of window perimeter around for each of those facade configurations. So I'm starting with an R20, but I end up with a range going from R15 in the best cases, lower bottom case, to something like R12 near the top. How significant is this? I'll show you a bit more in 2 slides. But it's something, okay, so it's a significant drop going probably down to 30 to 60, 70% of the initial values, down to maybe even 50% of the initial values. R12 is not very far from R21. And so that's the degree of derating that takes place. Whether that translates into a 50% increase in heating, most likely not. It's probably in the range of 5–15%. What happens with the NECB is that we're heading in the opposite direction. So the code is telling you, you need an R23 for those locations, regardless of the fenestration layout, regardless of those choices. So for the same fenestration and wall ratios and the same psi characteristics of those thermal bridges, this is what you would describe in your building specs, or this is how you would describe it to a contractor. You need to come up with an R37, an R30, close to, in 3 cases, about, more or less R40 in 3 cases. But the case with the very numerous individual, what we say in French, meurtrières, very narrow windows, you're looking at an R174. Once you're moving in the opposite direction, any type of, it doesn't have, those numbers are very low, the psi factors, but we have a lot of them and they add up. So once you start having significant weaknesses in your building envelope, any move towards higher performance is really a penalty. So I usually use these graphics to explain this to a client or an architect. So engineering students would be used to plotting R values on the x-axis and just using the inverse for the U factors on the y-axis. Those would be IP units. So there's a sweet spot where, as you're moving, I'm using this as a reference, if you're using curtain wall spandrel, you may have an R5 or R6, and you're still in the sweet spot of increasing the level of insulation by changing the technology. As you'd be moving to an R20, R23, you're still in that sweet spot. It's usually fairly cost effective. So any type of derating towards the left. So this is going from a U0 to a UT for energy simulation purposes. You may be dropping the performance by 50%, but compared to a spandrel, it's not necessarily that significant. You may have an energy modeler that's able to compensate with HVAC technology pretty readily, in fact. Once you move in the opposite direction, so you have a code requirement, in this case R23, I know I have thermal bridging. In some cases, I can mitigate it by eliminating windows or eliminating certain window configurations. You're necessarily moving in a direction, in the most optimistic cases that I show, that's an R38, but you can easily head in that direction. And the difference in performance in terms of nominal impact on the U factor, well, is going to be decreasing as I'm moving along. So you could say along the x-axis, that's cost and the complexity of building this. And on the y-axis, it's the actual impact for a cold climate of factoring in correctly or not thermal bridging or the quality of the envelope. So as you're moving beyond R23, you're probably, you keep the focus on maintaining an R23 as an overall UT value target, you're coming up with cases that are going to be extremely expensive, and we're coming up with cases where it is physically impossible to achieve. It's best to explain this using the equation. So if I have a 0.21 value here, and I'm subtracting thermal bridging, it's not complicated to understand that if this is equal to 0.21 as a sum, I have a U0 of 0, which means infinite insulation. That's not going to happen. If that number is superior to 0.21, then it's physically impossible to achieve a compliance of 0.21 or R27. As we're doing building stock assessments, this is popping up very, very often, especially for one-story buildings. One-story buildings will have a grade edge and will have a parapet edge. If you're talking about buildings that are 4 or 5 meters tall, this will be a significant impact. If you're looking at big box retail where the height might be 12 meters or even greater than that, then you have a lot more wall area to accommodate that thermal bridging, and you might come up with cases where it's economically viable to achieve prescriptive requirements. But in most cases, this is going to be very difficult for one-story buildings. I was really nice in my example by using some of the lowest values that were commercially available, that we have pricing on. These values, a simple switch to values, anything under 0.2 is pretty good. It's not the top of the line, but it's pretty good. And I'm not changing the window perimeter, so it's still very low in terms of psi factors. But these simple changes will for ASHRAE 90.1 will take me from R15 to something like R12 and R10. It's a bit more significant. You're still increasingly in the sweet spot. You're better off assessing thermal bridging and mitigating those thermal bridges as you can. Then if you're looking at the NECB, then we're not looking at R40s. We're in the 140, 180. In the top left corner example, there's no physical answer. There's no physically plausible solution to comply to code. Which essentially means the NECB 2017 and 2020 codes are really describing the conditions for a pure performance code. I have not come up with cases where it's cost effective to try to comply. And I and many others are confronted with clients that have a bit of a naive requirement. Let's make the building 35% better than code, but by all means, let's keep the NECB prescriptive requirements of building envelope. Let's comply to that, and then have to explain to them the implications of that, and they probably don't have the budget. And some very, very large clients, public clients in the country, have had to backtrack from those requirements. Not trying to be not trying to be difficult, but it's a challenge that no one has really anticipated, apparently, for the coldest of the climate zones in the country. I'm trying to access one of the questions here. A question from a non-NECB user: the performance specification required is the U value. Yes, let's close this. So the NECB, just as ASHRAE, has prescriptive requirements for building envelope. In the case of roof and walls, you would have a U value requirement. ASHRAE 90.1 and the Quebec Energy Code, these remain U factor requirements, U not. So these are those representative samples that describe the construction principle of that wall or that roof. It is not a UT requirement like the NECB 2017 and 2020, which are no longer just the U naught, the clear field. It's also factoring in linear and point conductances in the same number. And this will also set up the conditions for the reference building if you're using a performance-based. So in the case of the NECB 2017, the reference building would for climate zone 6 would look a lot like those facades, but all of the thermal bridging would be at 0 instead of those numbers, which makes it a perfect wall. Okay, I'm going to fill those questions as they come along. Oh, there's three minutes left. So, okay, so I'll be trying to speed this up. If I can shut the... Okay, quickly, 2 or 3 challenges that remain up in the air. That's something I think we can achieve within the next few months. Energy Plus in particular and OpenStudio have the possibility of accommodating multipliers and spanners to speed up the simulation process. If you have repetitive windows, repetitive floors, TBD will work in some of those cases. In others, we have to bring some minor changes. In others, like the internal mass solution and the zone multiplier, that's a biggie. So those would be something that we would have a hard time doing in a short lapse of time. If anyone wants to take that on, you can contact me. I'd be willing to accommodate them. There was a nice presentation yesterday from Design Builder on Kiva. TBD does the same. It generates automatically Kiva inputs and does a number of interesting steps, like estimating for you the exposed perimeter once you have walkout basements or sloped terrain, which is pretty heavily sloped, and you would have a full basement on one side of the building and a complete exposed area on the other side of the foundation. And so this will be done automatically for you by TBD for Kiva. There is a challenge with the building envelope thermal bridging guide where you do have psi factors, but you have to really pay attention to what are the elements that do characterize the psi factors, and here in yellow, versus the other elements which should be part of the Kiva model. So for those in the Energy Plus universe that are interested in both considering Kiva and psi factors, you need to sort this out. So this may result in something like a modification of the user guide to TBD to provide guidance for this. Okay, and the last, I'd say, major challenge has less to do with TBD and rather the point and linear conductance model that is presented. So this is in RP 1365 and the ASHRAE standard and so on. There's a nice comment by Aaron Berenian 2018 on this request to have thermal bridging processed in the Energy Plus core calculations. And we give our thumbs up, and you can go online and read this one. And we provided an extensive, not an answer, but more of a support to this question. And we started discussing a critical point, which has to do with maybe more of Michael Don's question initially. What happens when you have in milder climates where, maybe it's 2000 heating degree days or 1000 heating degree days, where you have significant thermal mass, or maybe it's an existing 19th century building that doesn't really have a clear insulation layer to derate. How do you factor in thermal bridging without modifying the transient response in a significant way? That's a good point. We recommend not to go down this path, but there's no easy solution out of it, apart from that second approach that is described in ASHRAE, which you leave the clear field description multi-layered assembly alone, but you add a sliver of a wall that represents all the thermal bridging. Let's say that's mainly concrete and steel. That may have a significant transient response that is, a transient response which is significantly different from the very thick, heavy, lot of thermal inertia, thermal lag in the main assembly. And there would be no point in trying to derate the major assembly with the thermal bridging. Might as well have this into two separate surfaces. And this would be more in line with Michael's question about having surface temperatures, maybe condensation assessments, if you are explicitly representing thermal bridging instead of derating. So that is something that's still up in the air. We fully support the idea that if Energy Plus wants to go down that path, we'd be happy in just canning TBD at some point if this is natively supported by Energy Plus, but we're not there yet. So, okay. Assuming the original code U and R requirements did not account for linear and point heat loss, are the incoming code UT values being increased now that the thermal bridging needs to be included? And the answer is no. So a couple of white papers and public review comments were submitted to the standing committee that writes the Canadian codes. And I think it was essentially set aside as being, well, it's up to the designers to design facades differently, or better mitigate the thermal bridging. But in reality, we're, especially on the building stock side, we're coming to the conclusion on a regular basis that there's no physical solution, or there's no physical solution or no cost-effective solution. So no, my initial assessment is that the 2017 and 2020 code don't factor in, they haven't lowered the R value in order to factor in the additional thermal bridging. So there's a second part to that question. My understanding is the original R value requirements were somewhat arbitrary and based on typical wall constructions at that time. I actually sat as a standing committee member in 2009-10. So the effective R values that were required actually came from ASHRAE 90.1, a draft version of the 2010 edition. And you had those exact values, but ASHRAE rolled back those numbers by the time they made it to the actual standard for public review. But the Canadian codes kept those numbers. So I would say, yeah, my general impression is that those values are somewhat arbitrary and not determined by any type of building stock assessment and practical assessment. I'm moving to another question. I was wondering why you chose to derate the insulation layer thickness rather than conductivity in TBD. So quickly, it actually does both. It tries to do the thickness first, and if it doesn't have enough thickness, then TBD will actually try to modify the conductivity. We're comfortable with that solution for cold climates, climate zone 6, climate zone 7 and beyond, 7A, 7B. Thermal mass doesn't seem to play a huge role once you're in the minus 25 degrees C in company. Once you're in milder climates, that becomes another issue. My understanding, okay, so the other question was, in my testing, I found thickness and conductivity adjustments do lead to different results when the insulation layer has meaningful thermal mass. I do agree, such as in a timber frame wall, and I was wondering if there was evidence supporting one approach over the other. We don't have a lot of sensitivity analysis there. Again, we tried to stick as close as possible to what codes require so that we don't introduce an artifact in our solution to support codes. We would rather support the codes to the letter and then have maybe a sensitivity analysis afterwards to show, well, this becomes an issue in milder climates. If you're somewhere in the southern states, I'm talking for the North American context. If you're in Arkansas or maybe parts of Texas, maybe this is not so significant and you shouldn't be modifying the thickness of assemblies. If you're modifying insulation, I'm not so worried. There's very little thermal mass there. But if you're affecting mass timber or you're affecting CLT construction, cross-laminated constructions, or rammed earth walls or adobe construction, this is not a good idea. So we actually do support you on that point. We do suggest that you shouldn't be using the derating solution, and ASHRAE 90.1 actually does accommodate the other solution, which is keep the original constructions intact, but do add these sliver of surfaces either near the slab surface or elsewhere, so you can actually factor in thermal bridging, which will be affecting at a very short time step the thermal conditions in the room without affecting necessarily the transient response of the other surfaces. So I have another question. Did you say that Design Builder will provide the linear thermal bridge links for your calculations, window perimeter, parapet links, corner links? My understanding is that yes. We have some exchanges with the Design Builder team a few weeks ago. This is my understanding. It's actually well documented on their online website, on their online guide. The best would be to contact either Design Builder staff or any type of rep. They would point you to the right direction. So yes, my understanding is that Design Builder does the automatic takeoffs. Do you have any comments for BEM in California? I have no specific recommendations or even detailed knowledge of what happens in Title 24. I suspect this is more Title 24 linked. You can reach, I don't think my email is on any of the slides, but you can reach me at denis@rd2.ca. So if you do have questions and you can point me in the right direction, I can try to help you how you could use TBD to solve your code compliance paths if you're heading down that direction. So my understanding of TBD is the identification of every change in the base vertical or horizontal plane. Is that okay? I'm not exactly sure what my understanding of TBD is. So maybe I'll just summarize in other words what TBD does. So if you have a default construction that applies to all roof surfaces, but some of the roof surfaces have HVAC components that are resting on supports, and you may have a roof curb, and the area is much smaller. TBD will actually do clone copies of each of those construction and make them surface specific. So the individual surface per surface construction layers will be derated to different degrees, which is what would happen in real life. So you would have changes in your sizing of HVAC equipment because both the peak and the annual loads will be changing on a surface per surface basis. If that's not the question, by all means, try to reach to me directly. I will just tap my email in the chat. So that would be easier. Oh, there we go. So Matt just did that. Okay, so I think I've answered all the questions for now. People are free to reach out to me directly if they have specific questions or they're unsure. I would recommend going through the online documentation for TBD first. A number of these questions would be answered there. But then, by all means, hope this was useful for you. And Matt, back to you.
Yeah, great. Thank you so much for presenting. That was an excellent presentation. I certainly learned a lot, and I'm looking forward to including that in the models that I make. I will end the webinar there. Thanks everyone for showing up. The recording will be posted on the IBPSA-USA YouTube channel within the next few days if you would like to follow up and rewatch parts of the presentation. So thank you and have a great rest of the day.
Thanks.